So you can see the metric, this is G00, this is G11, G22, G33, all other. So this is a diagonal metric, off diagonal entries are 0. You can see that the metric G00, G11, G22, G33, they do not depend upon time. So 1, 0, 0, 0 vector is a killing vector. I have not done killing vector, but doesn't matter, we will do it. So because the metric doesn't depend upon time, metric also doesn't depend upon phi. So we can immediately identify two killing vectors. But because metric doesn't depend upon time, what you can show is that if you have any geodesic starting from here at time t1 and ending up at time t2. So it's a geodesic, freely falling particles trajectory starting at time t1 and coming and ending up at here at this point at time t2. Okay. Now you ask, what about the geodesic with the same tangent vector etc., but which starts at time t1 plus delta t, when will it land? Obviously it will land at t2 plus same delta t. Why? Because the metric doesn't depend upon time. There's a time translation invariance. So if the particles started at time t1, ended up at time t2, then another particle which starts at time t1 follows the same geodesic, it will end up at t2 plus same delta t, because the metric doesn't depend upon time. It is that I used the fact that the coordinate time delta t up there is same as the coordinate time delta t when the light comes at the end. So because, and this can be done only if the metric doesn't depend upon time explicitly. And this is crucial for the Pound-Repka experiment. Only then you can say that square root of G00 c square delta t square is the physical wavelength there, and at this point square root of G00 at R2 c square delta, same delta t square is the wavelength below. So the delta t being same is because the metric doesn't depend upon time. Okay, so today what I will do is I will begin with the geometrical aspects of GR. So far we did elements of differential geometry, but we didn't connect it with GR. Right. So the first thing we realize by virtue of the equivalence principle, first thing is that existence of a space-time metric. Which tells me that given any two events, close by events, so this event and in any curvilinear coordinates, this event will have coordinates x mu, space-time coordinates x mu, and this is dx mu. Existence of a metric tells me that the proper distance, the invariant proper distance ds is such that ds square is and because you are free to choose any arbitrary coordinate system, Therefore, because dx mu transforms to dx prime mu under a general coordinate transformation to del x prime mu by del x alpha dx alpha, in order that this is invariant, g mu nu at x must transform to g prime mu nu of x prime. What is the relation between x prime and x? Same event in the old coordinate is described by x alpha, and that same event in the new coordinate system is described by x prime alpha. That is very important. And because of these two, you can immediately see ds square is the same, invariant. You just plug in there, you will find the same as g alpha beta prime at x prime. So, for our space-time, we cannot do relativity without the existence of a space-time metric. And this gets connected with special relativity because you can always choose a local inertial frame, you can always choose a freely falling frame or the local inertial frame, such that this event is described by zeta alpha, that is Minkowski coordinates. This is described by zeta alpha d psi alpha. So, in the local inertial frame, we find ds square is same as eta alpha beta. This is true generally. Even mathematical space-time with metric has this, but local Einsteinian equivalence principle guarantees that the same two pair of events in the local inertial frame, the proper distance will be this. Okay. Next geometrical property. Next geometrical property is the notion of how to take the tensorial difference of a vector field. So, if you are given a vector field v alpha of x, and it's a vector field at every space-time point, your vector is defined at another you have v alpha at x plus dx. But then, as we saw that in order to find out what is the differential of the vector that transforms like a contravariant vector, I have to parallel transport this vector. So, I have to parallel transport the vector here, so that after parallel transporting, its components are v alpha plus del v alpha, and only if I take the difference between v alpha x plus dx minus v alpha delta alpha, this differential is, so this differential is your capital D of v alpha, and that we saw is nothing but covariant derivative v alpha semicolon mu dx mu. And explicitly the covariant derivative is nothing but v alpha partial derivative So, there is an existence of a connection. In order I can subtract two vectors at two different points, there has to be a connection called, so this is the connection which is called the there is a connection called the christoffel symbol. And then yesterday we saw that in order this d of v alpha transforms like a contravariant vector, the christoffel symbols themselves must transform as follows. Under a general coordinate transformation. But then there is a term, additional term, which says so there is a inhomogeneous term that is there which renders the christoffel symbol not to be a third rank tensor. So christoffel symbol is not a third rank tensor. And yesterday we also saw, because of this transformation property, this quantity is a tensor. That means this object is a third rank tensor. Okay? Third property, that by virtue of the fact, I of course did not carry out the detailed derivation. I asked you to I asked you to prove that you take any vector field and take first covariant with respect to beta, then manifestly this is a third rank tensor, and you will show that this is proportional to, there is a plus minus sign, that this is proportional to and because plus or minus, and therefore if this is a tensor, this necessarily is a fourth rank tensor. So we said that there is a fourth rank tensor called the curvature, Riemann curvature tensor. Is defined everywhere in the space-time. And it is, and I laid down certain symmetry and antisymmetry properties. I asked you to prove it by going into a local inertial frame so that these two terms go to 0. And physical significance of the Riemann curvature tensor is the tidal force part. So here you work out the problem. We have already shown that for weak fields, G00 is 1 plus 2 Newtonian potential divided by c square. You can work out what are the dominant components of the Christoffel symbol. So you will find the dominant component of the Christoffel symbol is gamma I00 from this, I being spatial index. Find out the dominant component for the Riemann curvature tensor, and when you apply it to the geodesic deviation equation for non-relativistic pair of particles falling, you will actually see the tidal forces. The same tidal forces which make the oceans bulge out. So we all know physically that given the earth here, and when there is no gravity, the ocean would be having the same spherical surface. But when a heavy object like sun is this side, then the ocean bulge here and it gets bulged here, and this part gets compressed. So it is tidally stretched like this, compressed like this. And but earth is a local inertial frame. The earth is freely falling under sun and moon's gravity, but tidal, the Riemann curvature tensor is a tensor. If it is 0 in one frame, it is not. If it is non-zero in one frame, it is non-zero in all other frames. And if it is 0 in one frame, it is 0 in every other frame. So therefore, although earth is freely falling, tidal forces are there which says that the Riemann tensor is non-zero. So you can therefore carry out an exercise, and from the geodesic deviation equation, you exactly get back, you will find that these are the dominant component. If I remember, this will be the dominant component for static phi which doesn't depend upon time, and slowly moving pair of geodesic. You will find this will be the dominant component, and this will be related to the second derivative. Okay, so I mean, all right, it is basically phi ij will be second derivative of phi proportional to phi ij, which is the derivative of the gravitational field. So you will have phi by r cube term, gm by r cube term, which is the tidal acceleration. So that then you will see what is the physical significance of the curvature tensor. Okay. Let's pause a minute and make a connection. I mean, it's a pun, not the Christoffel tensor as a connection, but some physical connection. So note, at this point, you will be wondering that aren't there two independent geometrical quantities appearing? One is the metric tensor, which gives me a means of finding out the proper distance between two events. On the other hand, there is another geometrical entity I need, namely the Christoffel symbol, the connection, that will tell me how to parallel transport a vector, and also that will tell me how to construct another fourth rank tensor, namely Riemann curvature tensor. Are these different? I mean, are they different, meaning are they completely unrelated with each other? Yes, mathematicians have developed a whole class of space-time where they are not related to each other. But it turned out, in Einsteinian general relativity, they are related. So now I am going to tell you under what circumstances the connection, namely the christoffel symbol, gets connected to the metric tensor. But okay, so okay, but these are important. I will not erase it as of now, but I will erase one part. So although Einstein did not approach that way, because he was trying to make connection with Newtonian gravity, but we will, since today's thing is geometrical aspects, so we will use certain geometrical assumption. We will say that yes, gamma mu alpha beta minus gamma mu beta alpha is a tensor, but we will assume this tensor is identically 0. That means what? There is no torsion. So we will, first assumption is torsion is absent. But there are physicists who have said, how about including torsion and see how Einstein general relativity gets modified. So we will say torsion is absent. That's my assumption A. Meaning christoffel symbol is symmetric. Okay.
Is this something that cannot be verified unless we have more dimensions, or is it?
No, no matter which dimension you go to, you have to, in order to get a relation between the metric tensor and the christoffel symbol, you have to make at least two assumptions. So this assumption and the second assumption I am coming to. By the way, I mean, you can ask those who are interested in Kaluza-Klein theory, as you know, that Kaluza and then later on Klein, they added one extra dimension to space-time, and magically they got equations similar to electrodynamics and Einstein's GR under certain assumption. So you can ask, can we do something where in the 3+1 part of the space-time torsion is symmetric, but when in the fifth dimension it is asymmetric. So what will be the torsion in the fifth dimension? So such questions can be raised, and one might find some interesting structure. Okay, the second thing. Oh, by the way, I didn't mention another, a double role of metric. Yes, metric gives this notion of a distance, but other things also we have mentioned, but we should also highlight. Metric G mu if you have, then it, for every V mu, you can have a contravariant vector, which is obtained using the metric. And also for every contravariant vector, you can get, every covariant vector, you can get a contravariant vector using the inverse of the metric. By the way, I mean, it's a trivial exercise to show that the matrix inverse of G mu nu downstairs, that means G mu nu upstairs, also it transforms like a contravariant second rank tensor. It takes a little algebra to prove it. So remember, what am I saying here? We know that G alpha mu is a second rank covariant tensor, but it's not obvious that its matrix inverse should also transform like a tensor, but you can prove. And what is the definition of the G alpha beta upstairs? It's by definition is the matrix inverse. That means G mu alpha, G alpha nu is Kronecker delta, because this is the matrix inverse. Okay. And you can show that the matrix inverse G upstairs, it transforms like a contravariant second rank tensor. It can be proved, but it takes a little, so I don't want to spend time proving that. Okay. So the metric tensor does two things. It can find out the distance between two events, proper distance, and you can use the metric tensor to lower and raise the indices of vectors, tensors, etc. Okay. So, because the second property that I will assume is based on that. Second property. Now, we know what is d of v mu. We also found out how to evaluate d of a covariant vector. We also know how to find this. So, this we know is given by v mu semicolon alpha dx alpha, and this is also v alpha mu dx. And we have found out how to, what is v alpha semicolon mu, what is v mu upstairs semicolon alpha, we have figured it out. But someone will say that, look, if I have a metric tensor, for every v upstairs mu, I can construct v upstairs alpha. Agree? All right? So, someone will say that d of v mu by definition is d of g mu alpha v of alpha. This by definition, because v alpha's index raised using metric tensor will give you v mu. Similarly, d of v alpha by definition is d of g alpha beta v of beta. Here there is no assumption. This is strictly true, because if you have a metric tensor, you can use raising and lowering using the metric tensor. Okay? But now comes, this is what the mathematician will say, and this is what leap of imagination. Someone will say that, look, d of v mu itself is a contravariant vector. Therefore, shouldn't I get this by raising, shouldn't I equate it to g mu alpha d of v alpha? After all, dv mu is a contravariant vector. I can raise the index or lower the index. So, therefore, d of v alpha, if I raise alpha, shouldn't I get this? Similarly, shouldn't this be, so there is a question mark. Shouldn't I say that this is same as g alpha beta of d of v beta? Because if I am able to raise and lower a contravariant and covariant vector using the metric tensor, capital D of v mu, capital D of v alpha downstairs, they are also contravariant and covariant vector. I should be able to raise and lower indices using the metric tensor. And shouldn't this, okay, this part is not, shouldn't this two be equal? Shouldn't this two be equal? That's the question. It's not obvious that it should be equal. So, therefore, a theory, a geometrical theory where you equate this two and you equate these two is a geometrical theory which is where you don't equate these two. It so happens Einstein's general relativity, which is a physical theory, Einstein's general relativity will say, let's equate this two. Let's equate this two. But what does it mean? If I equate, for example, you can do the same thing with this, but I'll start with this. Suppose I equate, if G alpha beta of dV of beta is equal to d of G alpha beta V of beta. Suppose I say that yes, by lowering d of B beta with G alpha beta is same as taking d of the contravariant V of alpha. If this is true, what does it mean? But we know capital D is having the Leibniz rule property. So therefore, this by definition is same as d of G alpha beta. First capital D acts on this V beta, and then plus G alpha beta, capital D acting on V beta. By virtue of the fact capital D satisfies the Leibniz rule. It's a derivative operator, and all derivative operator must satisfy Leibniz rule except one derivative operator we encountered in differential geometry which doesn't exactly satisfy this Leibniz rule. What was that? Exterior derivative. We saw that exterior derivative of alpha wedge beta didn't exactly satisfy the Leibniz rule. There was a minus 1 to the power, if it is a p form, minus 1 to the power p. That was slightly different. Yeah. So therefore, if this is equal to then this must be equal to this. But this can happen only when capital D of G alpha beta vanishes. Okay? If capital D of G alpha beta vanishes, so this implies that capital D of G alpha beta must be strictly 0. But this is an additional imposition. If we demand that this is equal to this or this is equal to this, capital D of G alpha beta equal to 0, and similarly here we will have capital D of G mu nu upstairs must be 0. But what does this mean? After all, what is capital G of alpha beta? It is, here you have x mu, here you have x mu plus dx mu, you are parallel transporting, here you have the G mu nu of x, here you have G mu nu of x plus dx. To find out the differential, you parallel transport to this, and you are saying that it is G mu nu, the metric tensor is such that when you parallel transport this here and take the difference, it is 0. Or in other words, what this means is that everywhere the metric tensor has been generated by parallel transporting. That means D of G alpha is 0.
Can you repeat?
Yeah, okay. So, yes, so this is, I said a statement about metric tensors. I should have first said it in the case of vectors so that you would understand what I say. Suppose I generate a vector field which is strictly speaking same everywhere. Meaning what? That you take this vector, no matter which path you go by parallel transporting and go there, when you take capital D of V mu, it is 0. Or you don't have to do that. Supposing I have a vector field, now I take a full path. I will not just say I go to y mu. So this is a further away, y mu. Suppose I want that I parallel transport V of alpha x along this curve. So this is my curve C of lambda from x mu to y mu. I take V alpha x parallel transported so that I get V alpha of y. What equation will this satisfy? If I am completely parallel transporting, That means d of V alpha anywhere should be 0. It is the same vector. So the equation this will satisfy along the curve is that d of V alpha divided by d lambda must be 0. It has been parallel transported all along. Similarly, by imposing that capital D of G mu nu is 0 everywhere, that means if I know G mu nu at this x, I generated G mu nu everywhere else by parallel transporting G mu nu everywhere. That's what it means by saying capital D of G mu nu is 0. Okay. By the way, it is obvious in Minkowski's spacetime. In Minkowski's spacetime, eta mu nu is same everywhere. And eta mu nu's ordinary derivative is 0. So therefore, if you use equivalence principle, all these assumptions are natural. Because we have to make a connection with the equivalence principle. So if you allow equivalence principle, all these must be true. And that's the reason why equivalent demand of Einsteinian equivalence principle leaves us with no choice. It says that capital D of G mu nu better be 0. Okay. Capital G of alpha, by the way, before I go to capital G of alpha beta, I will say something which I have not said, because we are now talking about geometrical aspects of GR, and therefore this is also one geometrical aspect of GR which must be mentioned. You have done the geodesic equation, right? By the way, how did Bhashwati get to geodesic equation? By finding out the path between 2 points and extremizing it? So when in the tutorial you got the geodesic equation, which is d2x mu by d lambda square plus gamma mu alpha beta dx alpha by d lambda dx beta by d lambda equal to 0. This can be obtained by saying that square root of g mu nu dx nu from point 1 to 2, this path is the extremal. That means when you vary with respect to the path, it must be 0, and you can get this equation. Okay. Now I'll show you something very interesting. Supposing you say that there is a path. So this parameterized by the lambda real number, there is a curve. That means at any point, x mu of lambda is the coordinate of the along the curve. And we know that for a curve, at any point, you have the tangent. Tangent will be dx mu by d lambda. Agreed? So therefore, at any given point, let's say lambda 1, the tangent vector is dx mu by d lambda at lambda 1. That's the tangent vector. But suppose you say that I choose that curve, there's a special curve where the tangent vector is parallel transported along itself, along the curve. Okay? I want to know what is that curve for which the tangent vector at any point on the curve, next point I have parallel transported the tangent vector. But you have already known the machinery of parallel transport. That means capital D of d lambda, remember, any vector which is being parallel transported along the curve must satisfy this. So therefore tangent capital D of d lambda of the tangent vector, what is the tangent vector? D of x mu by d lambda must be 0. Okay? And you will find the same as the geodesic equation. It's obvious because call the vector, tangent vector v mu mu to be dx mu by d lambda. And what is this equation? This equation is nothing but v mu semicolon nu dx nu by d lambda, where v mu is, and what is this quantity? Dx nu by d lambda v mu comma nu plus gamma mu nu alpha v alpha. This into this will be d2x first term, and this into this is this term. So do this, I haven't done it fast, but do it. So therefore, what you see is the curve which extremizes the path, and that's why you call it geodesic, is also the path for which the tangent is being parallel transported. But this is true for ordinary flat space straight line, right? In Euclidean geometry, what is a straight line? It is the shortest distance between the 2 points. But straight line is also the fact that the tangent, meaning the direction of the straight line, is always straight. It is parallel transported along itself. Okay? All right. So these are the geometrical aspects, and that's why I have called this today's lecture as geometrical aspects of GR. So in other words, what we have just now proved is, oh, by the way, this statement following from this requires the Christoffel symbol to be related to derivatives of the metric, while this doesn't. The parallel transporting doesn't require any relation between Christoffel symbol and metric. The relation between Christoffel symbol and metric comes about only if you assume this. So various geometrical aspects, I am connecting them. I have said many things over the last 15 minutes. And therefore, if you want to study the geometrical structure, you have to go back to the recorded lecture. I've said many things, and each is, from the geometry point, are very important. Okay, now I will show that how capital of G of alpha beta equals 0. That means the metric tensor is such an object that is generated everywhere else by parallel transporting from one point. How this will immediately tell me what is the relation between the Christoffel symbol and the metric tensor.
Sir, one question.
Yeah.
I want to ask.
Yeah.
Can you explain how do you get the intuition that equivalence principle gives you the D of G alpha beta is 0?
Ah, yeah, good. Yeah. So what is D of G alpha beta? D of G alpha beta, by very definition, is nothing but G alpha beta covariant derivative with respect to mu dx mu. Agreed? So therefore, if this is 0 everywhere, that means it doesn't matter what dx mu you choose, this means that G alpha beta semicolon mu must be 0. But it should happen for every dx mu, any direction you. So covariant derivative of the metric tensor must be 0 if this is 0. And what is this object? Yesterday I had wrote down the expression. What is any covariant tensor? Its covariant derivative is G alpha beta comma mu minus gamma g minus gamma g, and then I will fill up the indices because I am taking with respect to mu, and alpha, lambda nu, lambda mu, alpha I have already taken, beta I have to take, beta, alpha, lambda. So this is the covariant derivative of the metric tensor. Okay. Now I will say what happens to this equation in the local inertial frame. Local inertial frame, at that point, Christoffel symbols go to 0. These two terms 0. and over the entire region of the Christoffel symbol, G mu nu is eta mu nu, but eta mu nu is constant, its partial derivative will be 0, so it has to be 0 according to Einsteinian equivalence principle. So again go back, what is Einstein equivalence principle? So that's very important, that's what I have been emphasizing. Einstein's equivalence principle is much more than Galilean equivalence principle. Galilean equivalence principle only says that if you drop any two objects in any gravitational field, the acceleration doesn't depend upon the inertial mass. Einstein realizes that acceleration, etc., you can't have a measurable notion if you use curvilinear coordinate system. So therefore, Einsteinian equivalence principle is no matter what your gravity is like, uniform, non-uniform, time dependent, time independent, you should be able to choose a small enough frame for a small enough duration of time such that the metric tensor inside, everywhere inside is eta mu nu, and at least at one point Christoffel symbol is 0. That is what is Einsteinian equivalence principle. And from that logic, we know that yes, in the local inertial frame, G alpha beta semicolon mu is 0, and therefore in any curve, and this is a tensorial equation, if it is 0 in local inertial frame, it better be 0 in arbitrary frame, and therefore this better be true all the time. By the way, this way of saying, at least I haven't seen in any book. Of course, the writers like Weinberg, Landau, etc., they knew it, they found it obvious, so therefore they never stated. But it is important to state explicitly, if you adhere to local inertial frame concept of Einstein, this necessarily must be 0. Okay, now I can erase that part. The dusters always get displaced. I try to plan it such a way that duster should be here, but I forget. Right, now we will see how, if this is true everywhere, is a tensor relation. So if it is true in one frame of reference, it has to be true in all frame of reference. Now we will see how from those equations I can find out how the Christoffel symbol is related to derivatives of the metric tensor. So let's construct this combination. So let's consider this combination. That result, that G alpha beta semicolon mu equal to 0, means that each of the term is 0. So sometimes people say, oh, if you were just using a identity that 0 is everything, how can you get some non-trivial result? Sometimes you can get non-trivial result by just summing up zeros. This is an example. Each term is 0. So someone will say, if each term is 0, what non-trivial thing can you get? We'll see that we will get some non-trivial term. So now expand each term. If I expand each term, what do I get? G lambda alpha semicolon beta, then minus gamma g, and I'll fill up the indices. So let's fill up the index. Because I am differentiating with respect to beta, then there is lambda here, so sigma, lambda, alpha. Then here, because I am differentiating with respect to beta, then first thing is what? Lambda as it is, and then alpha will be sigma, alpha. Then let's take a look at the other one, G lambda beta alpha. So therefore, you have G lambda beta comma alpha, and again minus gamma g, and since there I am differentiating with respect to alpha, alpha. Then the first term is lambda. So therefore lambda, sigma, sigma, and you have beta, beta, and then you have sigma. We have already taken lambda, sigma, and you have alpha is the derivative, so beta. So let's verify these two things are, you could have got it by interchanging beta and alpha. Okay, interchange beta and alpha, interchange beta and alpha, interchange beta and alpha. Okay. Then the final term, last term, G alpha beta, comma lambda, again. So this is alpha beta with respect to lambda, so lambda, lambda. Okay, so we have written down these two. Now notice, many of the terms will get cancelled. Okay, what are the terms that get cancelled? Look at this, gamma, sigma, alpha, beta, G lambda, sigma, and this will get cancelled because we are assuming that our Christoffel symbol is symmetric. So if Christoffel symbol is symmetric, that means gamma, sigma, alpha, beta is same as gamma, sigma, beta, alpha. Okay. This will not get cancelled. Both are negative signs, so that will not get cancelled. What will get cancelled? Look at this, minus gamma, sigma, lambda, alpha, sigma, beta, and this minus is plus, but that is minus, so this will get cancelled with this. Similarly, look at this, minus gamma, sigma, lambda, beta, G sigma, alpha, okay, and oh no, the last term, I think there's a mistake. This is a mistake, because if you say covariant derivative is lambda, lambda is here, okay, lambda is here, it should be alpha sigma, okay, because here it was G sigma, sigma, alpha lambda, and beta will be, so beta lambda, yeah, so this is, so there was a mistake in the earlier thing. Now look at this, it gets cancelled with which term? Yeah, this term. There is a minus sign here, minus is plus. So this term gets cancelled with this. I am assuming Christoffel symbol is symmetric, and G is anyway symmetric, so G sigma alpha is same as G alpha sigma. They get cancelled. So therefore, what are the terms that remain? We have, this remains G lambda alpha comma beta plus G lambda beta comma alpha minus G alpha beta comma lambda, and finally this and this, they add up because I am assuming Christoffel symbol is symmetric in the lower two indices, and therefore I get minus 2 G lambda sigma gamma sigma alpha beta. And this is 0. If this is 0, I find that I have got an equation which says that G lambda sigma alpha beta, that is equal to half of half of this. Sometimes, remember, Christoffel symbol is not a tensor, but sometimes people say that, you know, sigma is being summed, I can call it, sometimes it is denoted, it's a definition, is denoted as this. Uh, in the old books like Peter Bergman's book, they will call it sigma with a slash, with a vertical bar, alpha beta. The definition. Remember, it's not lowering of a index because gamma sigma alpha beta is not a tensor. It is a notation. So we have got this result, that this is equal to this. But someone will ask, but how do I get gamma sigma upstairs alpha beta? Because right now you have multiplied g lambda sigma and sigma is being summed over. But we have an inverse metric tensor. I can use the inverse metric tensor and get it. How? I will now multiply both sides, multiply these two sides by, remember, sigma is being summed over, but lambda is still free. I can therefore multiply g mu lambda, g lambda sigma, gamma sigma alpha beta, which will be half, because I have multiplied by g mu lambda, I get g mu lambda. Okay, and g mu lambda, g lambda sigma is an inverse matrix. Lambda is being summed over. So what is it? It's Kronecker delta mu sigma. So this is nothing but Kronecker delta mu sigma, because lambda is being summed over, and there g mu alpha, g alpha nu is delta mu nu. I had already written down. Using that, I get this is Kronecker delta mu sigma. And Kronecker delta mu sigma, sigma is being summed over. So therefore, the only non-zero term will be when sigma is mu. So this is same as, so we have got the Christoffel symbol in terms of the metric tensor and its derivative. So this is the relation between Christoffel symbol and the metric tensor and its derivative. And this was used when you extremize square root of g mu nu dx mu. When you say what is the shortest or longest distance, when you set this equal to 0 and use the thing, then you will get the geodesic equation, d2 x mu by d lambda square. This result is true only if Christoffel symbol is related to derivatives of metric tensor. Equal to this. Okay. Let's do some more geometrical aspects of GR. Let's at least be as much complete as possible as geometrical thing. Then there's still a lot of time. Then I can go to the physical, some physical aspects of something else which we have not so far talked about. So remember, when torsion is absent and under the assumption that local Einsteinian equivalence principle is correct, then indeed the Christoffel symbol is related to metric tensor and the derivative of the metric tensor. But if sometime in future experiments tell us, because there are people who are trying to do a lot of experiments to check whether Galilean equivalence principle is correct. If Galilean equivalence principle becomes incorrect, even Einstein equivalence principle will become wrong. Then what are the things that will still survive? What will survive is connection will be there, but the metric and connection, their relation will not survive. So probably then you have to say, oh, perhaps there is a torsion somewhere. That's the simplest modification you'll have to do to GR in case in future experiments. Long time back, TIFR, Ramnath Kaushik of TIFR had designed a Yachtverse modification of Yachtverse experiment at Gauri Badnoor near Bangalore, where his graduate students that time, N. Krishnan, Unni Krishnan, they were doing the experiments, and they had set up very good Galilean experiments results. But right now, if I remember correctly, it's 10 to the minus 14, I think, that the fact that all masses fall with same acceleration, it is to the order of 10 to the minus 14 have been tested somewhere in Louisiana State University or somewhere in Washington, where Ramnath Kaushik, after retiring from TIFR and IIA, he went there. So the bottom line is, so far, experimentally, Einstein's GR is consistent with all the experiments and astronomical observation. But as I said in my first lecture, a good scientific theory is that theory which can be falsified, where no theory can be proved. No theory can be proved. Today it is consistent. How do you know that tomorrow some experiment will not contradict the theory? A good scientific theory is that which in principle can be falsified. Someone will say, oh, string theory is not a theory then. No, string theory is also falsifiable. But to accept that experiments you required to falsify string theory, the energy you have to sort of achieve is 10 to the power 19 GeV. It is not possible today. Right. So now let's do some more geometrical aspects. These concern the Riemann curvature tensor. Riemann curvature tensor has another important identity, namely Bianchi identity. Bianchi identities say that if you take the Riemann curvature tensor R mu nu alpha beta and take covariant derivative of the Riemann curvature tensor with respect to, let's say, x gamma. Now what you do, you add by cyclically permuting the last three indices. This is 0. Okay. And then you proved, you'll say, oh my God, how will you prove it? It's a fourth rank tensor and its covariant derivative. So, okay, so let's just look at how the terms will be. R mu nu, alpha, beta, gamma. So this will be R mu nu, alpha, beta, ordinary partial derivative with respect to x gamma. Then there will be a plus gamma r term corresponding to upper index. I will not put down the indices, there will be indices. Then minus gamma corresponding to one of the indices, another minus gamma r which is to another index, and finally another minus gamma r. So one single covariant derivative has this term. How will you prove this? So what is the trick you will use? Local inertial frame. If you use local inertial frame, then at that point where Christoffel symbol is 0, all these terms will disappear. And then all you have to do is show that this part, when you do it, it's 0. Okay? Okay. So I will leave that exercise to you. But even that is non-trivial. But remember, just one partial derivative of this, you have to take the partial derivative of these terms. But of course, you have chosen the local inertial frame, so these two terms will be 0. But even then, you have to deal with partial derivative of these two terms. So, Landau-Lifshitz in his classical theory of fields, he gives you this trick. You see, Landau, you read any book of Landau, I mean, there's a joke. When I was in TFR, Virendra Singh, who had been the director of TFR some time, and many people consider, even I consider him as a very sharp guy. Extremely, anyway, I've told stories about Virendra Singh to you guys. So Virendra Singh in in TFR West Canteen, we were all sitting together. He had made this statement that not a single word of the Landau-Lifshitz books have been written by Landau, and not a single idea in the book was due to Lifshitz. Anyway, that's a joke. But anyway, you read Landau-Lifshitz, any volume, whether classical mechanics, fluid dynamics, any book, you will find there are deep physical and mathematical insights, where in classical mechanics, when I used to teach classical mechanics to MSc students, the rigid body dynamics, all the Eulerian angles, so complicated in Goldstein, Landau-Lifshitz will give the argument in one paragraph. Some people will find it difficult to understand that paragraph. If you go through it, you'll find it is an elegant one paragraph proof of all those which Goldstein takes 4 and 5 pages. Yeah, but yeah, it's okay. Is there anything else I want to talk about? The geometrical aspects of GR? Yeah, one more thing. One tensor which mathematicians never bothered to ever construct, but Einstein did it. That's why it's called Einstein tensor. Oh, did I? Okay. No, I have to do one thing before that, right? I have not yet introduced Ricci tensor and Ricci scalar. Huh? I have to do that. Without that, I can't introduce Einstein tensor.
So, sir, this Bianchi identity, is it true even if the principle of equivalence is violated?
Let me think. Yes, it is true, because the Riemann curvature tensor is defined using the Christoffel symbols and its derivative. And the Bianchi identity follows from this. The relation between Christoffel symbol and the metric tensor and its derivative is not assumed. So therefore, no, wait a minute. No, yeah, it's still valid. But although in my proof, I use the local inertial frame, but you don't have to. If you're bold enough, you go ahead and do it in any frame of reference. You'll get it to be 0. So you don't have to use the trick of local inertial frame. So there's something called Ricci tensor. These were all well known before general relativity arrived on the scene. Ricci tensor is obtained from the Riemann tensor by contracting the upper index with one lower index. So in our convention, there are many ways to define, they only change sign. So I will define the Ricci tensor R mu nu, probably the same as Landau-Lifshitz or same as Weinberg. I have forgotten it corresponds to which notation. This is, take the upper index alpha and contract the second lower index with the upper index. The fact that alpha is repeating means it's being summed over. Okay. Correct. Then once, so what is it? This is same as, if you want to write in terms of, this same as G alpha lambda, the same as this. Okay. Yeah. Mu is as it is, lambda has been raised, okay, and one raise and one alpha and nu. So let's see whether it is the same thing. No, this is not the same. We have to be careful. Have to be very, very careful in the indices. Mu is as it is. I want a raised thing, so lambda. Yeah, no, this is not the correct way of writing. Yeah, no, wait. Lambda is being raised to alpha, then there is mu, and then there is alpha, then there is nu. Yeah, this is correct. Okay. So R mu nu, Ricci tensor, is take the Riemann curvature tensor, contract the upper index with the second lower index, which is same as, after all, what is R alpha mu lambda? You take lambda, raise it. Lambda when it's raised is alpha, and then mu alpha nu. Okay. Okay. Now you can immediately prove that Ricci tensor is symmetric. That is, this is the same as R nu mu. Why is it so? So if you interchange, so why is it so? Because you look at this term and interchange mu. So I'll start from here. So G alpha lambda, R lambda, I'll consider this interchange nu alpha mu. So R nu mu by definition from this relation is G alpha lambda, lambda nu alpha mu. Agreed? I've just interchanged. But now one of the symmetry properties I asked you to prove is that this is same as G alpha lambda by pairwise. So if alpha mu comes here, lambda nu comes there, it's same, right? Alpha mu lambda nu, because of the symmetry property of the Riemann tensor. Okay. But this object, okay, is nothing but what do I want to prove? That R nu mu is same as R mu nu. This is what I want to prove. That means I want to prove that this object is same as this. Right? So you can see here alpha lambda is being summed over. So I can call this as lambda and this as alpha. The same as G of lambda alpha R lambda mu alpha nu. But G lambda alpha is same as G alpha lambda, so therefore these two are equal, and that proves that this is nothing but R mu. So Ricci tensor is very important because out of the curvature tensor is a fourth rank tensor. You have created a second rank tensor which is symmetric. Now why symmetry is very important? Because now I can create a curvature scalar. This is called the Ricci scalar. Ricci scalar R is, because it's symmetric, I can contract. Had this been antisymmetric, G mu R mu would have been 0. But because it is symmetric, I can construct a scalar out of the Riemann tensor. And you can see, you can verify that the only scalar that you can construct out of the Riemann tensor is this. In fact, that's what, when I was learning GR, I would try to modify gravity by adding something. But you can't. You can't do anything through curvature tensor. Whatever you do, you'd end up in the same curvature scalar R, same Ricci tensor R mu nu. Okay?
Of course, you can construct more scalars.
No, no, no. More scalar using curvature tensor. Using oh no, they are higher orders. I want to have by scalar meaning things whose derivative will not have higher derivatives of the metric tensor. Right, now I will define what's an Einstein tensor. Einstein tensor is denoted as capital G mu nu, probably to make it connected with gravity, and this is defined to be R mu nu minus half G mu nu. This is your Einstein tensor, which is constructed out of the Ricci tensor and Ricci scalar. And I will not prove it, but using Bianchi identity, again using local inertial frame so that it's simpler, you can prove that. So this along with the Bianchi identity both together, you can prove that G mu nu semicolon nu is 0. That means G mu nu upstairs is just raise the indices using the metric tensor. Then you can prove that G mu nu upstairs covariant derivative with x nu and nu being summed over, because nu is repeating, is being summed over. So Bianchi identity along with the definition of Einstein tensor gives you 4 divergence lessness of the Einstein tensor.
So in defining this G mu nu, what was the motivation for this minus half factor? I could have think of any other linear combination.
No, but if you choose not minus half, you will not be able to get this identity.
So that is the like physical.
This is very important. By the way, what does it remind you? G mu nu semicolon nu equal to 0. Good that you asked the question. What does it remind you? Is there something else which satisfies such a energy momentum tensor? So I have not yet introduced energy momentum tensor. Yes, in the remaining time I'll do that. But first of all, let me go to flat space-time system. Or shall I? No, let me introduce energy momentum tensor systematically. Otherwise, it will be hodgepodge. Yeah. So let me defer the flat space-time. I will introduce energy momentum tensor in a very systematic manner, because physics is where energy momentum tensors are. So let's see, is there anything else I wanted to talk about the geometric aspects of GR? Just this, that, remember this is all geometric. This is all geometry of the space-time. There is no physics, except at the back of the mind, we have assumed that Einsteinian Einsteinian equivalence principle is true. Otherwise, it's all geometrical aspects of GR. So far, the only physics that has entered is the assumption of Einstein equivalence principle. Otherwise, this is all geometry. And geometry by definition is mathematics. Euclid's geometry, yes, inspired from real life triangles, trapezoids, etc. on a plane, but essentially it's a mathematical subject with axioms and theorems. So this is so far is all mathematics, but eventually that's how physics is. I mean, there is no branch of physics you can do without having mathematics, absolutely none. So now I will talk about energy momentum tensor. So I'll erase, so those have been done. I'll erase this part of the board. Right. So now we come back to physics. Physics is what? Physics is all about energy, momentum, mass. These are all physics. I mean, the fact that if I want to move the duster, I have to impart a momentum, and once I impart a momentum, it has kinetic energy and so on. That's where physics is. So let's go back to our special relativity. Yes, we can do Newtonian analysis with momentum, energy, etc. But now that we are talking about the correct mechanics, we have to talk about special relativistic mechanics. Special relativistic mechanics, we know that if you have a free particle, then we all know from our undergraduate days that one of the things is that momentum vector P can be written as rest mass into the Lorentz gamma factor times dr by dt. Okay. This is the momentum, and then we know that this implies for a free particle the total energy is such that it is equal to p square. P square means p dot p, so it's mod p square c square plus m square c4. So kinetic energy, total momentum is given by that, where, yeah, I must mention, where the same as m into dr by dt, where m is m0, Lorentz gamma factor is simply square root of 1 minus v square by c square. This is by definition gamma m0. And you can show, you can plug in all these, you will find that this is same as gamma m0 c square, which is, that's why you will write it as mc square. You plug in all that, you will find that this is what happens. So for point particles, free particles, I just have to deal with its kinetic energy, its rest energy m0 c square, its momentum, etc. I can do it. But then someone will say that, look, your macroscopic systems are not a single point particle. It has extension, is made out of several point particles and so on. How do you describe the energy bulk momentum of big macroscopic systems? That's the first question. And how do you talk about the fact that they are not free? They are having interactions. So therefore, you need to, even in special relativity, you need to formulate it in a very special relativistic covariant fashion. And the first step, therefore, you do is you say that, okay, if I want to do it, first let us define the 4 momentum, which transforms like a 4 vector under Lorentz transformation as m0 c dx mu by ds, where ds is square root of eta mu nu dx mu dx. By the way, I am talking about special relativity or Minkowski space-time special relativity. There is only metric is eta mu. Because we understand the physics, as I said, physics is well understood in flat space-time using special theory of relativity. So let's first understand energy and momentum in the arena which we know well, namely inertial frames of reference. So all these are in global inertial frames of reference, and no, the gamma factor is hidden here. So p mu is rest mass into speed c dx mu by ds. Huh? See check what is P0. It will be energy divided by C. Let's see what happens. P0 C. What is dx0? Is C dt. So dx0 is d of Ct by ds. What is ds? So this is m0 c square dt by, what is ds? ds is square root of c square dt square minus dr dot dr, which is c square dt square, take it outside. So mc square dt by c square dt square outside is c dt. square root of 1 minus v square by c square. So dt dt cancels, one factor of c cancel with this is m0. And you get m0 c by square root of 1 minus v square by c square. For a free particle, this is energy divided by c. And because it is 4 momentum, we have each component of the 4 momentum has to have same physical dimension, and energy divided by c has the physical dimension of momentum. So everything is consistent. Okay? And this equation can be neatly written using p mu as eta mu nu p mu p nu is what? m0 square c square. The same equation can be written as this, and the beauty of writing it in this manner is it's completely Lorentz covariant. It's a Lorentz scalar, both sides are Lorentz scalars, but it's an identical equation as that. And you can very well imagine what happens in curved spacetime. In curved spacetime, all what happens is eta mu nu gets replaced by g mu nu. All right, so we understand for a collection of free particles, if you have a collection of free particles, you can write down, add all the 4 momenta together. But then someone will say that, well, if you have a collection of free particles, big object, some particle will be having momentum in this direction, some particle will be having momentum in other direction. So therefore this object, you can't talk about a single momentum for the object, they are all extended. And that is the reason why you define an energy momentum tensor. Remember, we are still talking about flat space-time, and flat space-time you can therefore sum up, and you have free particles, let's say, all kinds of trajectories going this way, that way. So n going from 1 to infinity, you can have infinite number of free particles, and you can write the energy momentum tensor Mn. Now Mn is a rest mass. I don't want to put 0. Mn are the rest masses, and you can write it in terms of dx mu ds, dx nu ds. There is some factors mc, I should write it as proportional to. There's some c factors, I don't want to carry the indices. And the interpretation to this object is T00, 00 index is becomes, I should mention there's a Dirac delta function also. There's also a Dirac delta function. Delta 4 of trajectory. Only if you are sitting on the trajectory, you will find the energy momentum tensor. Because if you have free particle going around, if you ask what is the energy momentum tensor at a point where there is no particle trajectory, it should be 0. So therefore there is a delta 4 x. So this is a function of x and time, x and t, and this is x minus the xn trajectory ds. Anyway, those who are interested in getting all the factors right, read Weinberg's book. The best discussion of energy momentum tensor is in Weinberg's book, the 1972 book of General Relativity and Cosmology. Okay. T00, when you put 00, it is all dt, 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 and we have seen P0 is the energy. You will find T00 is the energy density, or call it energy density at position x at time t. Energy density is same as mass density into c square, because mc square, E equal to mc square. Then you come to what is T0I. What is the interpretation of T0I? It will be dx0 by ds is related to energy, but there is also nu equal to I mean dxi by d tau. So therefore, what is it? It is the flux of energy in the ith direction. So it is the flux of energy, in the ith direction. Yeah, go ahead.
Like in special relativity, the energy momentum has one Lorentz index. So, if one Lorentz index, like P means.
It's a 4 vector.
Yeah, 4 vectors.
Because it's a single point particle is moving, one 4 vector is enough.
But when you go to general relativity, there are like 2 Lorentz.
No. You still have, for a free particle, even in general relativity, you have a 4 momentum in curved spacetime, 4 momentum in curved spacetime. Is P mu by definition m0c. Now it is dx mu, general arbitrary coordinate system, square root of g alpha beta dx alpha dx beta. This is your ds now. You still have only one index, where x's now are curvilinear coordinate system. So if you have a single particle or 2 particle, you can just do everything with P mu. But
What is the motivation of constructing this 2 Lorentz index T mu?
that's what I said, that if you have a collection of many particles, some particle moving in this direction, some particle moving in that direction, a single index will not suffice, because it doesn't have the entire object is not moving in one direction. Some part, you can think of a soap bubble or a sponge, every part moving in arbitrary direction. So when you are talking about a macroscopic system made of many degrees of freedom, like a fluid dynamics, you have to necessarily introduce energy momentum tensor, or in fluid dynamics it's called stress tensor or something like that. In physics we call it energy momentum tensor. The engineers will call it stress tensor. Right. So
like one direction for area and one direction for the flux.
exactly. So that's the thing. So what is T0i? T0i, take the ith direction and take the area normal to the ith direction and ask, what is the flux of energy flowing in this direction? That is the physical interpretation of T0i. Now comes, okay, T0i, but what about Tji? Remember, I, j, k, they run from 1 to 3. Mu nu run from 0 to 1 to 3. Okay. Ij run from 1 to 3. So if I ask, what is Tji? Tji is the flux of jth component of the momentum in the ith direction. So again, you take the ith direction, have an area, ask, what is the flux of jth component of the momentum going across the flux? That is the interpretation of Tji. I am not writing it, but is understood. Now you will say, okay, T00, T0i. Then you ask, what about Ti0? What is Ti0? Ti0 is the momentum flux. Ti0 is the momentum flux, but momentum flux must be energy flux in the ith direction. Why? Because energy, when it moves, it carries momentum. Mass going in the particular direction is same as momentum, and therefore Ti0 is same as T0i. And energy momentum tensor you can prove for normal matter with conserved momentum and energy, T mu nu must be equal to T nu mu. Okay. All right. So this is energy momentum tensor in flat space time. But now Einsteinian equivalence principle, you say that very good. When you go to curved space time, what do we do? Einstein's equivalence principle says that wherever you have metric tensor eta mu nu replaced by g mu nu, and if there is a derivative, you replace by covariant derivative. Okay. Here I will take a pause and say if you have a collection of particles moving randomly, you can prove that this is correct from the conservation of del T mu nu by del x nu for a collection of particles for which no external forces are there, where momentum and energy are conserved. You can prove that del T mu nu by del x nu, nu being summed over, is equal to 0. This corresponds to local conservation of energy and momentum. Just like local conservation of charge was what? Del G mu by del J mu by del x mu is 0. That's the local conservation of charge. You did tutorial problem. Del J mu by del x mu is 0 is the local conservation of charge. Then of course from that you can prove that Q, the total charge, which is defined to be J0 integrated over space, is also conserved. Similarly, from this equation you can prove that total energy is conserved, total momentum is conserved, and so on. Now comes the local conservation of energy and momentum. If you write down in curvilinear coordinate system, what will happen? What is the principal equivalence principle tell me? All you have to do is, instead of ordinary partial derivative, you put the covariant derivative. So in curved space time, your local conservation of energy and must look like this. And this, as Vishnu was saying, it has a resemblance with this. The Bianchi identity result corresponding to the Einsteinian tensor. Now, just yesterday I was going through some as to who did what, who should we give the credit to, Hilbert or Einstein. There's a big controversy actually. There are some people who claim that Einstein got some terms which are wrong. People say no, it was Hilbert who got it wrong, waited for a letter from Einstein, then he corrected it. There's a big controversy as to the correct equations of general relativity. Is it to be attributed to Einstein or to Hilbert? This controversy is still raging. So I will not make a comment. I am not a historian of physics, so I will not make a. So there's a controversy that who got the everything about general relativity correct. It is well known that first few papers of Einstein about general relativity were wrong. That is true. But Einstein was trying it out. He was, because remember one thing, any new physics cannot be derived from old physics. You have to give your own assumption. So Einstein was trying out various things, and the beginning papers, there were a lot of mistakes. Eventually, at some point in 1915, he got the correct equation. But some people say that only when he received the letter from Hilbert stating in other way the correct, he published his paper. Some say no, Hilbert had not got it. So we should not get into this controversy. For us, what is more important is what is correct general relativity. And it's amazing that whoever realized first that whether Einstein or Hilbert, that conservation, local conservation of energy and momentum and Bianchi identity must be put together so that we have an idea about matter deciding what the geometry of the space-time is, and geodesic equation telling me that if there is geometry, how the trajectory of a particle which is not acted upon by any force, what should be the trajectory of the particle, that should be determined by space-time geometry, while space-time itself should be determined by the energy momentum tensor. Okay? So that is the situation. Now, Hilbert, the reason I was referring to the history is I am going to give you a method of obtaining the energy momentum tensor given the Lagrangian density of matter using a technique which is attributed to Hilbert. Okay? And that's the reason I was trying to see that if Hilbert did it, how much of the general relativity was done by Hilbert, and that's when I came across this controversy. But before I talk about given a Lagrangian density, how to derive from it the energy momentum tensor, which is attributed to Hilbert, and that method is so beautiful that is impressive. One must give credit to Hilbert that he found out a beautiful way of obtaining the energy momentum tensor. I'll talk about, but probably it's already 1:15. But before I take that, I must tell you some example of energy momentum tensor of fluids, continuum fluid, and that should be talked about because they play a very important role when you are trying to find out objects, forming black holes, the cosmology, and so on and so forth. So some examples, which can be, by the way, derived from all these. Weinberg derives all that from first principles. So we are now talking about continuum systems, fluids. So if you have dust-like fluid, imagine a fluid which is dust-like. What is dust? The chalk dust. Chalk dust, if you look at it carefully, you'll find dust particles are randomly moving, but the random motion is so tiny that pressure is zero. I mean, we all know from our school days, the kinetic theory of gas tells me what is the origin of pressure and temperature. In kinetic theory of gas, we know that the atoms and molecules in a jar, they are randomly moving, and it's the random motion which appears to us like pressure, it appears to us like temperature, and so on. Dust is a fluid where the random motions are negligible, so that the pressure is negligible. So pressure equal to zero is dust-like matter, and dust-like matter, you can imagine that if you have a dust-like matter and you have set up your coordinate system, origin, and you take a small volume element of the dust, so that the volume is delta V, and therefore if the density is rho, mass of this element will be rho delta V. This can have a bulk velocity V. It can be moving. Oh, this is volume and this is vector is V, or call it U. Then the momentum density for this element will be m into U, which is nothing but rho the volume element into U. This is the momentum for this object. So this is the momentum of this element. So therefore momentum density is rho into U. Rho into U is the momentum density. Okay. But now you ask, what is the energy momentum tensor for this? Remember, T00 must be equal to energy density. T0i is the flux of energy in the ith, or same as ith momentum density and all that. And you can therefore convince yourself that the energy momentum tensor T mu nu for dust is simply rho u mu u nu. This is for dust. So if your having a frame of reference, and at any given point the density, mass density is rho, then with respect to if you at that point suppose it has a 4 velocity u mu, then energy momentum tensor for dust like matter is mass density times u mu u nu. Okay. There is no pressure because, as I said, dust by definition is nothing but the random motions of individual constituents that comprise of the dust. Random motions are negligible compared to energy carried by the bulk flow. On the other hand, if you have perfect fluid, the perfect fluid energy momentum tensor is pressure plus energy density. Oh, by the way, if T00 has to be energy density, I should multiply by c square. So rho is the mass density times c square is the energy density. I am talking so far about flat spacetime. So the perfect fluid, the energy momentum tensor is given by this. Anyone who wants to know the energy momentum tensor, the best book is Weinberg's book actually. He gives thorough analysis of energy momentum tensor. So sometimes people write papers without not realizing what is this P, in which frame P has been constructed, which frame energy density has been constructed. Weinberg gives a thorough explanation of that. So I'll interpret it. What is this P and energy density? But first of all, I have to tell you what's a perfect fluid. So a fluid by definition is at any given point, apart from energy density, momentum density, it has a bulk flow velocity, and the flow velocity is u mu. The question is, what is a perfect fluid? Perfect fluid is that fluid that at a given point you have a flow velocity and you sit along with that means you have a frame co-moving with the flow velocity. In that co-moving frame, if density and the mass density or energy density, pressure, they appear isotropic. It doesn't depend upon the direction. Such a fluid is called perfect fluid. So in other words, perfect fluid is that fluid for which when you go at a given point to a co-moving frame, in that co-moving frame, measure the pressure and energy density. P and energy density are measured in the co-moving frame and they don't depend on direction. Such a fluid is called perfect fluid. Okay. You can see that dust is a special case of perfect fluid. Why? But the moment you set pressure to be 0, you get back your dust. So dust is also a perfect fluid, but with pressure is equal to 0. Okay. You can similarly find out the energy momentum tensor of the electromagnetic field. Okay. Electromagnetic field also, you can find out, was there a problem given on finding the energy momentum tensor for electromagnetic field? Like for example, momentum density for a electromagnetic field is given by the Poynting vector, c by 4 pi E cross B. If you have electric field, magnetic field, c by 4 pi, or I don't remember the factor, proportional to c into E cross B gives you the momentum flux called the Poynting flux. While the energy density of electromagnetic field is given by E square plus B square by 8 pi. That is the energy density of electromagnetic fields. And you can similarly write down the full energy momentum tensor of the electromagnetic field. All right, I think I'll stop here because it's nearing 1:30, and but you can ask me any questions. Tomorrow I will give you Hilbert's derivation of finding out the energy momentum tensor given any Lagrangian density for the system. It's called a local conservation because it doesn't tell you what is the global energy or global mass, go back to your electrodynamics. So, yeah, good that you asked me, because it's very important. Sometimes if you are not careful, you might deduce wrong conclusions. So, let us go to electrodynamics. In flat space electrodynamics, the local conservation of is written as this 0, which if you expand it in expansion form, it is nothing but del J0 by del T 1 over C plus divergence of J is equal to 0. This is the expanded, these are both equivalent. But this is not global conservation of charge, it is local conservation of charge. In one of, somewhere Feynman talks about it. It's a beautiful example, he says, to distinguish between global conservation law and local conservation law. See, Feynman was a master of physical picture. I'll give you that physical picture. So, by the way, this is local conservation of, it follows from Maxwell's dynamics. But supposing we didn't have this, we say that charge of a system, even macroscopic object, charge is conserved. Supposing you say that if you take a body, its charge, it's conserved. But Feynman points out that suppose I can think of a situation where charge is conserved, but there is no local conservation. How? So you have a object here having charge q, it disappears here suddenly, appears somewhere, then also charge is conserved. Because it has disappeared here, but it has appeared here. But this is not local conservation of charge. Because what happened from here to here, you don't know. It disappeared here, it appeared here. Local conservation of charge tells me, in order this to happen, something must flow from here to here. And this equation tells you that flow, that in a small region, charge density J0, this is the charge density J0, can be decreasing because the current is flowing out of the surface, divergence of J equals 0. So this is local conservation. It is telling me that yes, from here total charge is decreasing because charge is crossing a surface and appearing somewhere. From here itself you can find out that integral of J0 over entire volume, call it Q, this is conserved. dq by dt is 0. Why? Because dq by dt is, when you take time derivative, inside, then it will become partial derivative del J0 by del t d cube x, but del G0 by del t is same as minus C divergence of J is del J0 by del t. From this you can prove, substitute that, you will get minus C divergence of J volume integral. But divergence of J volume integral by Gauss's theorem is J dot integrated J dot to the surface element, and you take surface to infinity. At infinity, any physical field J must be 0, so the whole thing is 0, and so therefore dq by dt is 0. So in other words, from local conservation, meaning if J0 is decreasing, that means del J0 by del t is negative, what it means is divergence of J must be positive, because so that it is flowing out. So that is local conservation. From local conservation, in flat space time, you can derive global conservation of charge. But the other way around is not true. You can have a global conservation where charge is conserved, it disappears here, appears somewhere else. You don't know what happens locally. Has it flowed out? That you can answer. So this Feynman was, his pictorial way of understanding was something great. But by the way, Feynman also has a lecture series on gravitation, but there he is not that pictorial. So I read Feynman's lectures on gravitation thinking that he will give a pictorial way of giving general relativity, but he gives an alternative way of understanding general relativity. Not pictorial, but alternate. By the way, is somewhat outdated. His lectures on gravitation is outdated, but yeah, it's interesting.
So the definition, the way you have defined a perfect fluid, does it also mean that a perfect fluid is frictionless? There is no dragging force.
Yeah, so what this tells me, isotropy is very important. By definition, the perfect fluid is that where in the co-moving frame, pressure and energy density must not depend upon direction. So if there are internal friction which are directional, if there are internal friction which is direction dependent, this thing will not be happening. But Weinberg himself introduced a concept of bulk viscosity. So he generalized perfect fluid and put in bulk velocity, and he did some work on cosmology introducing bulk viscosity.